Good morning all. So, we will continue our discussion on analog electronics, and today we will be discussing about the small signal characteristics of BJTs. So, we have figured out what is the symbol for BJT and how it should be biased, right. We have seen that a positive voltage should be connected across the base emitter junction, which is around 0.7 volt, right. And also we have seen that collector to base voltage should be reverse biased. So, collector potential should be higher than the base voltage. So, this is the corresponding circuit for the NPN transistor and this is the corresponding circuit for the PNP transistor. Now, starting from the large signal model, this is our large signal equivalent circuit, where the base emitter junction is modeled by a diode and the collector to emitter junction is modeled by a dependent current source. So, this is complete large signal model and this is the complete large signal current, right. So, this is how our biasing circuit should look like. We should be having a base to emitter potential and also having a collector to emitter potential. Now, this is our small signal model, right. So, what is the small signal model? That we will consider that this small signal model at the Q, right. So, what we will consider that all the DC sources is having all the voltage sources grounded. So, that we do not need to consider the effect of the DC, we will only consider the small signal AC circuit and its effect. Okay. So, if we consider the base and emitter, so base voltage, that is VB, and the small current flowing through it, that is IB, and this will create one resistance. Okay. So, this resistance is modeled by a input resistance, that is R pi. So, R pi is nothing but the equivalent base to emitter resistance. Similarly, at the collector side, what we are modeling? We are modeling a dependent current source, that is IC, and IC is equal to GM into VBE. If we talk in terms of VBE, it is GM times VB. If we model this in terms of IB, it is beta times IB. Okay. So, the circuit will replace this two port network and other associated RAs, RL that will be connected. Okay. And we will try to solve the KVL and try to find out the output voltage V0. Clear? So, in place of this BJT, we will replace this BJT with its corresponding model. This model could be IB dependent or could be VBE dependent. Okay. Both are okay. If suppose your VB is given, we will use this model. If suppose your IB value is given, we will use this model. Okay. So, it is up to you depending on what information is available to you. Clear? So, we will be seeing that how to solve the small signal gain. Last day we discussed that we can arrive this is a complete large signal model and this is the transfer characteristics, right. This is known as the, or we can also say input output characteristics. Why? Because you see this side I am having VB, VB is my input and this is my output, output means this or VCE. So, this is input versus output plot. This is not, it is not like a one in x axis it is time, this is not timing diagram. Okay. This is a input versus output. So, overall this is a common emitter amplifier and what you can see, if your input is low, this BJT is off, your output is high, and if your input is very high, this BJT is fully on carrying the maximum current and your output is low. So, it is just like a, the full scale characteristics is like a inverter characteristics, right. In inverter, digital inverter, what we have seen? If we give a 0, we get a 1, if we give a 1, we get a 0. So, you can also see that if my input is rising, output is falling. If my input is falling, output is rising. So, we can understand that they are in a 180 degree out of phase. Input and output are phase shifted. If input is rising, output should fall, and if input is falling, output should rise. Okay. So, this they are phase shifted, and that will be modeled by the minus sign in the small signal gain. That minus sign correspond to this 180 degree phase shift. Okay. And that we can arrive from both large signal model as well as from the small signal model. We can also find out the large signal output voltage and take a derivative. We can also arrive a small signal gain. Okay. So, both are acceptable, but if it is a complex circuit, then it is easier to make a small signal model, because then it is a approximation, right. You approximate all the exponential equations to a simple ohmic equation, right, V is equal to I R, linear equation. So, this is our complete circuit, complete bias, including the coupling capacitor. Why the coupling capacitor are used? We have already discussed, to connect with input and output stages and to make sure that my DC bias is not affected. Okay. So, the job of this coupling capacitor is to make it sure that the whatever we are connecting, be it a voltage source or be it a next stage load, it should not disturb my Q point or DC bias. Only it will behave like a short circuit when the AC input is connected. So, it will let the AC input to pass, but it will block the DC input. And what is the job of this bypass capacitor? To bypass the emitter resistance. Why? Because we have seen that emitter resistance is helping to make the circuit stable against thermal runaway, but it is reducing our small signal gain. So, while the AC operation it will be shorted, but while the DC operation it will remain there. So, we get the advantage of both. We get the circuit stable at DC point, but we get the larger swing at AC signal. Okay. So, that way we will start our DC analysis first. We will solve the circuit, we will open the capacitor and we will find the Q point, IC Q and VCE Q. Then we will start our AC analysis, we will sort the coupling capacitor and draw the equivalent circuit, and we will replace this BJT with its small signal model and we will solve for the small signal gain. So, this is our steps. Now, this is one complete circuit and it is the equivalent circuit. You see, we have separated the open the cap. Okay. So, this circuit we will solve to find out the VCQ and ICQ. Okay. So, all the values we will try to find out. This is the first step. So, once this is done, then we will proceed towards the next step. Now, in next step what is said, that all the DC voltage sources should be considered grounded. Why? Because we have already calculated their effect. Now, I do not want this, I want only this. So, how to do that? If there is any DC sources apart, this is input signal, this is signal, this is not DC source, this is AC signal. So, all the DC sources should be shorted to ground. If there is any current source, it should be open. So, what we are doing? You see, we are sorting the VCC. Next, all the capacitor are sorted. So, this circuit you see, this R1 and RE they are connected to ground, and this R2 and RC they are also connected to ground. So, if you fold them, they comes in parallel, right. If you drag this here, So, they will come here, right, is not it. So, that is read on here, right. From the base this is R2. So, this should be R2 and this is from collector. So, this should be RC and this is ground, clear. So, all of this ground means all of them are actually sorted, but rather than sorting them a separate ground symbol is used, clear. So, this is same like this is also same, all the points are sorted and is connected to ground. This dot means sort, okay. So, this dot means sort. So, clear this. So, you see the real circuit, this node is not grounded, but while doing the AC analysis we will consider this as if AC grounded. This is in reality this is not grounded, but because we have already considered the DC part, this part is already considered. So, as if we will be considering that okay, let us start from 0 and let us calculate only the small signal, and then this small signal we will add it here to get the total current. This is our final objective, to get the total current. Now, we are doing this in two part. In first part we are considering only the DC, in second part we are considering only the AC. So, for first portion AC signal does not exist, this is opened. In second part DC signal does not exist, it is considered as ground, okay. So, do not get confused, and if I ask you to draw a common emitter amplifier, if you draw this circuit, this is actually wrong, because this is not the actual circuit, this is a equivalent circuit for only AC. So, sometimes I see that I ask you to draw a common emitter amplifier and you draw this kind of circuit with voltage source grounded, then it will not work, right. It is in cutoff actually, because in real circuit there is something else, that is this, okay. So, please understand that this is a model for a certain condition, not the total condition, clear. So, what we are doing, the voltage source VCC is sorted to ground, because we are only interested to see the effect of this, not the effect of this. Now, this voltage comes in parallel, this resistance comes in parallel, right, R1 and R2 comes in parallel, that we have also seen. Last day we discussed na VB, VB and R Thevenin. What was R Thevenin? R1 parallel R2, that is coming, clear. Next is what? RE is sorted to ground. You see there in this model RE is not there, because this cap is sorted now, okay. So, in this DC I have a RE, but in the AC circuit there is no RE, clear. That is because of this cap. If this cap was not there, suppose this cap is not there, then you have to consider RE, right. If this cap is not there, there is in AC circuit RE will be remaining there, no one to sort it. So, this depends on your circuit. Is there any bypass capacitor? If bypass capacitor is there, then RE will not be there. If bypass capacitor is not there, you have to draw the RE, clear. Next is your output. You see RC is my resistance at the collector. So, this is RC, and I in addition I also have a load resistance. That means, suppose this amplifier is driving another stage. So, this another stage may have a equivalent resistance, that resistance is modeled by this. So, what is happening? This node is grounded, this node is also grounded. So, they comes in parallel, right. Now, let us solve this circuit, okay. So, what is the total output, total load at output is equal to RC parallel, it is written R3, you can write RL also, you can write this RL. So, RL. So, this is our complete R out. And how much current is flowing through this? If current flows in this direction, this is positive IC, right, but current actually flowing in this direction. So, we will consider that minus IC is flowing. So, what will be my V 0? Minus IC into R out. My voltage is equal to I into R. What is my I? This terminal total current flowing is IC. So, this current plus this current equal to IC, and so if I replace this by a single resistance, then only IC will flow, that we are doing. Agreed? So, the equivalent resistance, this we are modeling with a single resistance and we are naming this as R out. When they are parallel, two separate current is flowing, but if you add them, what you get? KCL IC. So, if you make them equivalent RC parallel RL, then what is the current it should flow? There is no way to go, na? The same current should flow through collector. So, it should be IC. So, what is the voltage drop here? IC into R out. Now, what is your IC? You know, suppose your input side voltage is VBE, then your IC is GM VBE, that you term it as I. So, this is minus GM R out VI. So, what is your gain? V 0 by VI is equal to minus GM R out. So, AV is equal to minus GM, what is R out? RC parallel RL. So, this is our hybrid pi model, and we have seen that what are the values of this. What we have seen last day, GM is equal to IC by VT, R pi is equal to beta by GM, or you can remember beta is equal to GM R pi. R 0 is equal to roughly, you can neglect VC because VA is very large, early voltage, IC. Generally VA is negative, so it is, we will take the positive value only. Now, can you tell me, this is the resistance that when we look from the base, right? If we look at the base terminal, what we are seeing? R pi, base resistance, right. So, similarly, if we look from the emitter terminal, we will see a emitter resistance. So, it will be RE, clear. And when we are looking from the collector terminal, we are seeing the R naught, right. This R naught, this is actually when we are looking at the collector terminal, right. So, R naught is VA by IC, this is quite large, right. From the current also you can understand that the current is flat here. So, this resistance is very large, right. Now, can you tell me between R pi, this R pi and RE, which one is smaller? Just guess. RE is smaller. Why? Because RE is equal to, say, base emitter voltage Vx by IE. Now, this IE is very large, na? The emitter current is the maximum compared to the base current. So, roughly IB is IE by beta plus, okay. So, this R pi, your resistance is equal to voltage by current. If current is small, this resistance should be higher, right. So, R pi is roughly beta times higher than R e, agreed, because this current is small, this current is more. So, these values will go down and this value is small I b. So, this R pi will go down. So, roughly R pi is equal to beta times R e. Okay. Why? Because emitter current is roughly beta times I b. So, resistance should be inversely proportional, right. Resistance is equal to V by I, inversely proportional. So, if I am having large current, its internal resistance, this R e, it is internal resistance, it is really as if not is any resistance is not there. We are thinking that this junction will offer me this resistance. So, these are our model parameters. This is our Gm is equal to Ic by Vita, Ic by Vt, and R pi is equal to Vt by Ib, and it will come by beta by Gm, right. And Re is equal to roughly alpha by Gm, or this relations you see Re is equal to alpha by Gm, alpha is equal to roughly 1, right, 0.99. So, you can approximate it as 1 by Gm, and R pi is equal to, it should be beta times Re, I told you, no. Okay, it is coming, the relationship should come, no. The emitter current is roughly beta times Ib, Ic and Ib nearly same, Ic and IE is nearly same. So, this relationship also holds. If we approximate, if you consider 0.99, that is exact, you can approximate close to 1. So, this is our relationship. So, you see exact R pi is equal to beta plus 1 Re, okay. And we have relationship between beta and alpha like this, beta is equal to alpha by 1 minus alpha and alpha is equal to beta by 1 plus alpha. So, these are some relationship that you will be familiar with. So, let us consider how to calculate this Gm value, that Gm is equal to Ic by Vt we have calculated, no. How to arrive on that? We have discussed this last day. So, let us solve this today. So, let us assume that total base emitter voltage is equal to DC part plus a AC part. So, total is equal to DC plus AC, right. Now, similarly, total collector current Ic is equal to Is exponential total emitter voltage by Vt, right. So, is equal to Is e to the power, this I will replace with this equation, Vb plus small Vb by Vt is equal to Is exponential Vb by Vt into exponential Vb by Vt. So, this term we know, this is our capital Ic is equal to this, right. So, this is our equation 2. So, we will replace this with this is equal to Ic e to the power Vb by Vt. Now, you know that e to the power x, if you consider the infinite series, you have done this in your mathematics class, this is 1 plus x square by factorial 2 plus x cube by factorial 3 and so on, this is infinite series, right. Now, see if your x is approximately 0 or very small, this you can, these higher terms you can neglect, is not it. Suppose your x is very small, then x square will be even smaller. So, in that case Ex is equal to, this is approximation. Now, see if my VBE is much smaller than V t. What is V t? Thermal voltage is equal to K T by Q, right. V t is equal to K is Boltzmann's constant, T is absolute temperature, Q is charge of electron. So, this comes nearly equal to 25 millivolt. So, if your V b is much smaller than that, then you can approximate this as very small value, right. In that case, you can approximate this exponential as a series and neglect the higher terms. Okay. What we have discussed, that small signal analysis. I discussed this in even before, no, that input signal should be small. Why small? So that we can approximate it as a linear model, clear, and that is also coming matching here, that V b should be small. So that V b by V t is much smaller, and we can approximate this exponential series as 1 plus x only. So, what is x? V b by, clear. So, if you multiply them, what you get? I c, which is the my DC part, plus I c into V b by, so this is my AC part. So, what we arrived? I capital C is equal to capital I capital C plus small I c, right. Now, this small I c is equal to this I c V b by V t. Now, what is your GM? GM is equal to I c by V b is equal to so we have done that this formula GM is equal to I c by V t or roughly 40 I c, that how to derive that we just did it. So, now can we arrive the R pi? Can we calculate the R pi? How to calculate the R pi? I b is equal to I c by beta. Now, what is my I c? I c is equal to I c plus small I c by beta. So, this I b is total, this is total, small I subscript capital B, we have told the notation, na? This is total current. So, it has a DC component plus a AC component. So, this is the DC component and this is the AC component. So, small I b, this portion is equal to small I c by beta. What is small I c? We have just derived. Small I c is equal to I c V b by V t, I c V b by beta V t. Now, what is R pi? V b by I b. So, you divide this V b by I b, what you get? Beta V t by I c. Now, I c by V t is G m, it equals to beta by G m. So, we arrived R pi is equal to beta by G m or beta is equal to G m R pi. Easy, right? Clear? Now, how to calculate R e, emitter resistance? Same way, you should have a relationship of between I e and I c. What is the relationship? I e is equal to alpha I c, I c is equal to alpha I e. Okay. So, from that you will arrive the V by I e or the emitter resistance. So, that is done here. I is equal to I c by alpha and then I is equal to I e by V t into V b. So, R e is equal to V b by I e. We are trying to find out the emitter resistance between the emitter and base junction. So, which voltage to consider? V b. This emitter resistance we are trying to find out between the base and emitter junction. The base resistance we are trying to find out between the base and emitter junction. So, the input voltage Vx is Vbe for both the cases. Okay. And as we have just discussed, because emitter current is larger, the emitter resistance should be the smallest. Okay. Emitter resistance is the smallest, R pi is the medium and R c is the highest. R c means R naught. R c means looking in resistance between collector to emitter, that is R naught. R naught is equal to V A by I c. So, you see all of these values, they are at the which point? Q point. Up to this any questions? Clear? Okay. So, you just do not need to worry about what is small signal analysis. This is if you follow the simple step by step. First, what is your step? First you try to calculate all the DC conditions. Clear? Done. Then all the DC sources, voltage sources should be shorted to ground, and now I will be only considering the only AC signal, and then I will add them and I will arrive the total current. And how to derive all this expression? We have just derived that Gm is equal to Ic by Vt, R pi is equal to beta by Gm, and Re is equal to 1 by Gm roughly, because alpha is nearly equal to 1, Re is equal to alpha by Gm or nearly equal to 1 by Gm. So, these are the relationship, and relationship between R pi and Re is, as Re is beta plus 1 time Ib. So, R pi is beta plus 1 times Re. Now, while doing the AC signal analysis, we should separate the AC signal and the DC signal. How to do that? All the DC should be sorted. So, this VCC, it is sorted back to the ground. Physically we are not doing this, do not think that physically we will sort it, no, this is a on paper and pen and paper. On modeling you are doing this, physically if you do that, your circuit will be killed, right, it will be in cutoff. So, this is not physical, this is only calculation. Okay. So, what you are doing? All the sources are sorted to ground. So, this RC we can model it like this. So, then we will solve this and we will try to find out what is the output voltage, and then we will find out the what is the small signal gain. Okay. And we will replace this BJT with its equivalent model. Now, suppose let us consider that there is no early effect. So, if it is in, then this IC will be flat, na? Then do you have any R naught? No, this is infinite. So, if you have no R naught, then will you draw that R naught? It is infinite. So, actually you are not drawing that. If you are considering that there is no early effect, this is ideal condition. So, your R naught is infinite. So, there is no point in drawing this R naught between collector and emitter. This actually we will consider open. So, otherwise what we should do, that we should consider R naught. Now, suppose there is one RC. So, if this is grounded, this will come as, suppose this node is grounded, emitter node is grounded. So, this RC is connected to VCC. In doing the small signal analysis, this VCC is ground. So, we will just flip it and connect it to the ground, right. So, we will write the RC. Suppose no output is given, means no RL is there. So, what will be your V0 now? Minus Gm into RC. So, V0 is equal to minus, this is, what is this current? This input side, this is base side, right, this is collector side, this is emitter side. Base side and emitter side, what is this resistance? R pi, and what is this voltage? Vb. So, this is Gm Vb. So, this is my current, this current is flowing in this direction. So, this is flowing in this direction. If it was flowing through this direction, my V0 would be positive, but it is coming in opposite direction. So, this V0 is negative. So, this is minus current into resistance. So, current is this. So, what is my AV and what was my original circuit? Original circuit was like this. This was our original circuit. What we did? This we replaced with this model and we connected this RC, right, and we shorted this VCC. So, RC is connected back to the ground. So, we have connected the RC to the ground. So, this GM into minus GM into RC, this is for which BJT? Ideal BJT, considering R naught as infinity. Now, let us say that this is a real BJT and consider the early effect. Now, your current is something like this, okay. You have an early effect. So, what you will have to consider? This R naught you will have to now consider, and this emitter is virtually grounded. So, RC will come in parallel to this, clear. So, this will now become R naught. What is the value of R naught? VA by IC, and from collector to ground another extra resistance RC. Now, this circuit will be modified by RC parallel. So, this is considering, please take a note, do not just sit. So, simple, if I do not consider R naught, my gain is minus GM RC. If I consider my R naught, my gain is GM RC parallel R naught. My AV is equal to GM RC, and because it is phase shifted, a minus sign will be there. Why? Because common emitter amplifier is a inverting. Now, suppose in addition you have a load resistance. From the collector terminal, this load is grounded. From the collector terminal, this emitter resistance is grounded. This R naught is emitter is grounded. So, R naught is also grounded, and this while doing the AC analysis, this VCC is also grounded. So, all of this comes in parallel. I am making it complex one after another. First we considered no R naught, then we put R naught, but it comes in parallel. So, circuit is just parallel. Now, I have put another RL, this will also come in parallel. So, what will be happening? Another thing will come, that is parallel, but is my equation going to change? It is same thing, right. So, I will be having another parallel resistance, that is it, but the concept remain same. So, if we have a load resistance, then my AV is going to be minus GM RC parallel R naught parallel RL. Suppose you are not considering early effect, then it will become minus GM RC parallel RL, R naught won't be there. If you have infinite resistance, you just open it, right. So, exactly what we are doing the same thing. You see, we have redone the circuit to find the AC equivalent circuit, VCC is sorted to ground. So, this RC comes in parallel, and if we have R naught, so RC comes in parallel to R naught. Is it tough? Just simple KVL and KCL. So, what we are doing? We are modeling this with an equivalent resistance. What is this equivalent resistance? Equivalent resistance of these two parallel resistance is R naught parallel RC. If we replace these two by a single resistance, then how much current should flow? IC current will flow, and IC is equal to GM into VB, that is it. So, what is the voltage? Voltage is equal to minus IC into R equivalent. What is R equivalent? R naught parallel RC, just simple parallel circuit. In reality, is it parallel? In reality, it is not parallel, but in the AC model it is parallel. Why? Because in AC model what we are doing? This DC source we are sorting to the ground. So, in the AC equivalent circuit, this is equivalent circuit, not the real circuit, always keep this in mind. In the AC equivalent circuit, they are coming in parallel. Why? Because we are only interested in AC, we are not interested in the DC. So, all the DC sources we are neglecting. So, finally, what is our output voltage? V 0 into V pi. V pi is actually this VB, you can model this as VB and RC parallel R naught. So, your gain is minus GM RC parallel R naught. So, let us stop here today and we will continue from this.